In this video, we're going to derive Heron's formula. So let me just write that down. Heron's formula. So what is Heron's formula? Heron's formula is basically the formula for an area of a triangle. So how about we just start out by drawing a triangle? And so I'm going to say that the triangle looks something like this. All right, just can be any triangle. All right, and we're going to say that this right here is point A, this is point B, and this is point C. And opposite of point A, so opposite of point A, we're going to have side length A right here. Opposite of B, we'll have side length B. Opposite of C, we have side length C. So the whole idea of Heron's formula is that you can find the area of a triangle just if you know side length A, side length B, and side length C. In other words, you can find the area of a triangle if you just know the three side lengths of a triangle. That's the whole idea of Heron's formula. And so, how can we derive the area of a triangle in terms of just the three side lengths? Well, we could start with something that we know about the area of a triangle, which is we know that another way to express the area of a triangle is we could say that the area of a triangle is 1/2 AB sine of theta, right? That's one way to express the area of a triangle. And also, pretty much what theta is, it would be the angle between A and B. So between A and B, this angle right here would be theta. That's pretty much what theta is. And so we know that this is one way to express the area of a triangle. And so notice, all we have to do is we just have to find what theta is in terms of A, B, and C. Once we have that, we have the area of the triangle in terms of A, B, and C. So in order to do that, we need to find how theta is related to A, B, and C. So pretty much how are A, B, C, and an angle of the triangle related to each other? Well, in order to do that, it's just the law of the cosines, because the law of the cosines relates the three side lengths of a triangle to one of its angles. So we know that the law of the cosines is just going to be c squared equals a squared plus b squared minus 2ab cosine of theta. So this right here would be the law of the cosines, right? Pretty much for in this case as well, that's how that would work. Now, this is pretty much it. And if you're confused about like where this and this comes from, like if you're just not sure why this area of the triangle would be valid, and you're not sure why the law of the cosines works, I actually have videos on where the area of a triangle like this comes from, and also derivation of the law of the cosines. So if you want to see those, if you're just curious about like why is this true, then I will put video links down in the description if you want to know what that is before moving on to the next step in this. Anyways, continuing on with the derivation. Pretty much all we have to do is if we solve for theta and substitute theta into here, then we can just find what area is in terms of A, B, and C. So we just got to start by solving for theta here. And so the first part, we could first solve for cosine of theta. When we solve for the cosine of theta, we get the cosine of theta is equal to c squared minus a squared minus b squared divided by negative 2ab. So that's what happens when you just solve for the cosine of theta algebraically, right? Now, before we solve for theta, notice what happens when we do solve for theta. We are going to get cosine -1 of something, right? But the idea is that if we get the cosine -1 of something and we substitute it for theta into here, we're going to be doing the sine of the cosine -1 of something, which involves some more complicated trigonometry that I don't really want to get into. So let's try and find a little bit more of a simpler way to substitute theta into here. How about instead of substituting theta for something, we substitute sine of theta for something? I mean, we know how sine and theta and cosine theta are related. In fact, they're related by, let me just show you. They're related by the fact that the sine squared of theta plus the cosine squared of theta equals 1. That's how sine of theta and cosine theta are related. So if we just use the idea and write cosine of theta as sine of theta and substitute it into here, then that would work. Now, here's probably going to be a nice way to do it. How about we make this cosine squared of theta and make the sine squared of theta so the substitution can be easier? So to do that, I'm first going to start by making this cosine squared of theta. So in other words, when you solve for that, cosine squared of theta equals, pretty much, it's the numerator squared, right? Divided by the denominator squared. And when we square a negative value, it always becomes positive, right? And pretty much this is going to be 4a squared b squared. So that's what happens when we square the denominator. So this would be cosine squared of theta. Right here we're going to find sine squared of theta, right? Square both sides here. So a squared equals 1/4 a squared b squared sine squared of theta. So that's a squared. Now, the idea is that the cosine squared of theta is equal to 1 minus the sine squared of theta. Right, we're using this identity. So let me just rewrite that as that. Instead of rewriting a whole nother line to do that, I'm just going to write it like this. Right, 1 minus the sine squared of theta. Right, that would be the same thing. And solving for the sine squared of theta, we would get that this is equal to 1 minus this thing right here. So let me just write that. Right, and so this would be the sine squared of theta. And so all we have to do now is substitute it into this equation right here. In fact, I'm going to just make a dashed line so we can separate these two. Right? So all I got to do now is I got to substitute this into sine squared of theta. So this is going to be a little bit of work, okay? It's going to take up a little bit of space, so I'm going to try to write as best as possible. So a squared equals 1/4 a squared b squared. Actually, you know what? This might be easier to see if I write it this way. I'm going to write this as a squared b squared all over 4. So I'm writing this as a fraction times the sine squared of theta, which is, so I can fit this quite efficiently, 1 minus c squared minus a squared minus b squared squared all over 4a squared b squared. So this right here would be the substitution for sine squared of theta. And so this is the area of a triangle in terms of a, b, and c. And specifically, it's a squared. It's the area squared. So what we're going to do now is we're just going to try and simplify this as best as possible. So to simplify this as best as possible, why don't we just first start by doing distribution, okay? So when we're doing distribution, basically the whole idea is we get a squared b squared over 4, right? So that's pretty much just that times 1. Minus, okay, so now we get this fraction times this entire thing. But it's actually really nice, because notice how a squared b squared cancels out with a squared b squared. So we're just going to get 4 times 4 in the denominator. So this right here is just going to be 16 in the denominator, right? And then pretty much since a squared b squared canceled out, it's just going to be this in the numerator. So we get c squared minus a squared minus b squared squared. So this right here is what we have. We can combine these fractions by multiplying both the numerator and denominator right here by 4. And so when we combine those fractions together, we're going to get this. Right, we're going to get, let me just see, 4a squared b squared minus this part right here, c squared minus a squared minus b squared squared, all over 16. So this right here is pretty much what we have. So what do we do now? Look, how can we continue this? Like, can we just take the square root of both sides and just hope for the best? No. It turns out there's actually something here going on that you may or may not see. And it's really cool, actually, if you see it. But if you don't, it's okay, because some people might see what's going on here based on the amount of experience they have with solving problems that are a little bit more on this sort of level. Believe it or not, there is a difference of perfect squares here. A difference of perfect squares. So you see, this term squared, this squared minus this squared. It's a difference of perfect squares. In fact, the idea of difference of perfect squares, I'm assuming you know this, but the idea is that if you have, no, wait, let me rewrite that. The idea of difference of perfect squares, it's a difference of perfect squares. Just like that. And you can rewrite this as a minus b times a plus b. And I'm assuming you guys know this, but that's the whole idea of a difference of perfect squares. You can just rewrite it like that. We're going to apply that same concept to the numerator right here. And by the way, to conserve room, what I'm going to do is I'm going to write the 16 as 1/16. So 1/16 times, right, this is a difference of perfect squares. So the square root of this minus the square root of this times the square root of this plus the square root of this. Okay, so 2ab minus this, which is going to be c squared minus a squared minus b squared, okay, times, okay, this is going to take up quite a little bit of space, but I think we're just going to be fine. We'll just move back up to the top later. So this, all right, and then it's just going to be 2ab plus, we won't need parentheses for this, it's just going to be c squared minus a squared minus b squared. So you can see how it's just going to be that. All right, specifically, there's the minus sign for it, there's the plus sign for it. I could put I guess putting a parentheses here might help because you can clearly see where it is. You can see it's this minus this times this plus this. And so that's the difference of perfect squares going from this to this. That's the whole idea of what we just did. Now, the next step might be to kind of rearrange this a little bit. So let's just kind of rearrange this a little bit. So when we rearrange it, we're going to get 1/16 times, okay, so when we rearrange this, I'm going to rearrange this in a specific sort of way so you guys can see what's going to happen next, okay? Because it takes a little bit of work to really see what's going on here, but really I'm going to rearrange it like this. Okay, I'm just going to rearrange it like that. So this right here is what we have in the first parentheses. In the second parentheses, I'm going to rearrange it like this because you guys will be able to see what I'm pointing to in the next step, right? So we get this, okay? So this is what we get. Okay? I rearrange it like this purposefully, okay? So that's pretty much just rearranging them. Now that we have this, there's something really cool here. Once again, notice how we have this and this. Most of you guys are probably familiar with what these two things are. Instead of this being a difference of perfect squares, it is now a perfect square trinomial, basically, isn't it? So in this case, I'm going to use black, we have this, which we know we could write that as this, a squared plus 2ab plus b squared, right? That's just a perfect square trinomial. It's just a plus b times a plus b, right? And the same thing for a minus b. It also is a perfect square trinomial that results in. So a minus b times a minus b. You get a squared minus 2ab plus b squared. As you can see, we can apply these concepts to what we have right here for both of them. And so this might help us, right? We don't know if it's going to help us, but remember, the whole goal of what we're doing now is we're just trying to make this look as simple as possible. We're trying to go from something more complicated to something more simple. And we're really trying to simplify it by doing this. So a squared equals, we still have the 1/16 right here. And what we have right here, it's going to be a plus b squared minus c squared, right? Because we're just rewriting that as a plus b squared. Right here, we get c squared minus, or that's not it. I meant to write a minus sign. Minus a minus b squared. We pretty much rewritten that as that, rewritten that as that. What do we have now? What do you guys notice right here with this step? Now we have yet another difference of perfect squares, except we have two of them. This squared minus this squared minus this squared. So we have two difference of perfect squares, right? So we have two difference of perfect squares. That's all that's really going on here. And since we're going to run out of room, I really want to finish this in a good sort of space. I'm going to rewrite this at the top right here, okay? This is going to take a little bit of time. I'm going to rewrite at the top, okay? All right. So I'm not going to erase the bottom. So to rewrite it at the top. So because we won't have enough room at the bottom. All right, we're really getting there. Okay. Whole idea is I'm just going to rewrite this at the top so we can continue. (1/16) times a plus b squared minus c squared. Right, we have that term times that term. So we have c squared minus a minus b. And we're definitely going to finish before then, by the way. So I've almost rewritten everything that we had right here. There we go, right? Okay, we won't need this because it's already at the top. Now we continue. We've gotten this far. It's a difference of perfect squares. So pretty much the whole idea is we're going to write it like it's a difference of perfect squares. Right? We still have the 1/16 right here. All right? We're just going to change this. Pretty much just factor this. That's basically what we're doing. And I think that this is wrong, by the way. I don't think this is square right there. I think I meant to put it there. So we just do this. That's what I meant to do, right? So hopefully that didn't confuse you. So what do we do now? This is going to be a plus b minus c times a plus b plus c, because it's a difference of perfect squares. So a plus b minus c times a plus b plus c. There you go. It's a difference of perfect squares. That's how we can change it. Right, for this next parentheses, c minus parentheses a minus b times c plus a minus b. So now that we have that, looks even more simpler than we had at the top. In fact, let's just expand this right here. C minus a plus b is just going to be b plus z minus a, right? B plus c minus a. So now that we have this, can we really make this any simpler than it already is? It's kind of like already completely factored out. What can we do? We can do something. Notice how in all of these terms, what's the relationship between all of these terms? It's a, b, and c either being added or subtracted to each other. That's all it is. And we know an idea where a, b, and c are all being added together. That's just the perimeter of the triangle. A plus b plus c is the perimeter of the triangle. So let me just write that right there. The perimeter is just a plus b plus c, right? In fact, I should have written this higher because I wanted to use it. But I guess I'll just use it in the notes right here. But p equals a plus b plus c, well, right here is the perimeter of the triangle, isn't it? In fact, let's do that when we continue on to the next step. That's just p. So if this is the perimeter of the triangle, if this is p, then what's this in terms of p? Well, if we know that the perimeter of the triangle is a plus b plus c, then to find a plus b minus c, we have to subtract 2c on both sides. Right? Just get rid of that minus sign, it confuses some people. When we subtract 2c, we're going to get minus c right there. And then, of course, we just have a plus b. In this case, it's a plus b minus c, right? Equals p minus 2c. That's it. This is p minus 2c. Right? So this is going to be p minus 2c. This is going to be, in this case, it's b plus c minus a. So instead of doing minus 2c, we're doing minus 2a. So it's going to be p minus 2a. And same thing here, since we're subtracting b, it's just going to be p minus 2b. Right? We use that same idea to find p minus 2c, to find p minus 2a and p minus 2b. Just have to keep making sure I'm not going off screen. I think I'm going to be good. And yeah, that's pretty much the whole idea of that. So I can erase it now. There we go. That's the whole idea of doing that. So now, just the perimeter of the triangle is just a plus b plus c. So not really, we kind of are making it a little bit more simpler by doing this. Again, this is still 1/16 equals a squared, equals the area squared, interestingly enough. Now, how can we make this even simpler? We can't distribute the 1/16 to all this, because these parentheses are being multiplied together, not added. So we can't distribute the 1/16 across these, except we can kind of do it. Check this out. If we do this, in fact, yeah, actually I'm gonna do it this way. Yeah, we'll have enough room, so this is fine. Check this out. This right here, it's equivalent to what we have here, because 1/2 times 1/2 times 1/2 times 1/2 is 1/16, right? If you do 2 times 2 times 2 times 2, you get 16 in the denominator. So this works, right? That's the whole idea. It's not distribution, but it's using the idea of multiplication, 2 times 2 times 2 times 2 to get 16. And that's the whole idea of what this is, right? I'm pretty sure you guys can see that if you multiply these 2's here, you get 1/16, just times what we had here. All right, so why did I do this? Well, notice how in all of these cases you get p over 2, p over 2, p over 2, p over 2. P over 2 is basically half the perimeter. And there's this idea that we like to use where pretty much half the perimeter is denoted as S, where S is, they call it the semi-perimeter, which means half the perimeter, right? Semi means half of the perimeter. So that's what S equals. It's S equals P over 2. In fact, I'm going to write that right here. I just didn't want to write it above this, but that's the whole idea. It's half the perimeter. And so we could use this idea and apply it to here. Remember, S is just half the perimeter. So we could write it as a squared equals, now when we do this, there's things being multiplied together. So in this case, we have to think like that. So right here, p over 2 minus 2c over 2, right? We do p over 2 minus 2c over 2. That's how we would expand that out. P over 2 is S, because that's half the perimeter. 2c over 2 is c. P over 2 is S. This stuff right here works the same way as what we had here. P minus 2c over 2, p minus 2a over 2 works the same way. In this case, you're just going to get p over 2, which is S, 2a over 2, which is just a, so we get S minus a. And the same thing here. This is p minus 2 over 2. P minus 2b over 2. It's just going to be S minus b. That's it. Now that we know that, just got to take the square root of both sides to solve for area, because this is pretty simple looking. We just get S times S minus a times S minus b times S minus c. Look how cool that is. This is the area of the triangle in terms of the 3 side lengths of the triangle. And where S, all right, let me just write what S is. Again, just so it's really clear, S is the semi-perimeter, which means half the perimeter of the triangle. And remember, half the perimeter means a plus b plus c over 2. How cool is that? We went from some weird, crazy algebra to this. That is the area of the triangle in terms of the 3 side lengths. You might be wondering, why didn't they teach us this before? I mean, I knew all 3 side lengths of the triangle. Why did they teach us 1/2 base times height, where I had to know some sort of other length in the triangle? Why didn't they just teach us, oh, if you know all 3 side lengths, let's find the area of the triangle? It's because in order to figure this idea out, you have to go through all this complex algebra, not complex, but complicated algebra to get here. They didn't want you to use a formula without knowing where it comes from. But as you can see, look at this. This is the area of the triangle in terms of all 3 sides of a triangle. That's it.